How do I do exponent? Add exp. Exactly. Add exp, open parenthesis, and I'll divide at the end by RT, open another parenthesis. G is D3 minus G ideal gas, which is at P, which is F6. 5? Yeah, F5, thank you. F5 divided by R and divided by T, which I guess I can take it as B3 plus 273.15, close parenthesis, close parenthesis. Okay, what is the answer that the illustration in the book gave us? Right there, 6.7 megapascals. What is that? 6.7 megapascals. Okay. Daniel, you have no. Anybody has any questions? Okay, Jessica looks like she needs more time. Mine.
We chose an ideal gas package. Would it just give us the G value without having to factor in the RT onto a P value?
Yes, but remember, you have to have the same model for the real fluid. Good question. And you'll see a discontinuity there. If you use an activity coefficient model for the liquid phase and ideal gas for the vapor phase, or any other, or a different model in the vapor phase, because of the difference in the models, you have discontinuity between vapor fugacity and liquid fugacity.
Gotcha.
Jamal, question? No, never mind. Where did you lose me?
I was reading
You're reading what?
I was reading D3 is
He accidentally misread what he said.
B as an
Okay. So that will be the first part of your homework problem. But we can do a lot more than just find a simple fugacity. We can generate how the fugacity changes as we change pressure from low pressures where we are gas, transitions to the vapor pressure, we have the equilibrium between the two phases, and go high pressures where we are liquid solid.
Why does the P low affect the fugacity?
It doesn't. That's what I'm showing you, that whatever I use here, I will get G at P the same.
No, if you change P low, it'll change the fugacity.
It shouldn't.
It'll change
Okay, maybe in the last few digits a little bit because of calculation. Okay, yeah, in the last two digits. Computers don't have infinite accuracy. That's one. Yeah.
So
Yeah,
just
it'll
do
change
P
a
low
little.
1.
Here is the one that your text had, that the steam table had. Okay. Changes a little. Let's go back. All right. Save this. Let's call it, what's the next homework going to be, 5 or 4? 4. So homework for problem 1. Is that an easy homework problem to do? So for problem 2, let's generate a graph of fugacity against pressure at 300 degrees C. We can do that with a little bit of work. So let's exit the spreadsheet. And I'll go back here to the real fluid. And in this case, I'll be changing the pressure myself. I'll keep the temperature at 300. So I want to give the pressure, instead of having it calculated as the vapor pressure. So it was vapor pressure because I specified the one here which made it equilibrium. Let's instead specify, I don't know, a low, let's start from a low pressure, I don't know, like 10 kilopascals. Oops. And then delete this and put pressure 10 kilopascals. So delete the vapor fraction, put pressure 10 kilopascals. Okay? All right. Now, automatically everything within works. And remember, fugacity, and by the way, what was the calculated fugacity? Is that a surprise? At low pressure, at 10 kilopascals, what kind of behavior do we have? Ideal gas. What do you get? Fugacity equals pressure. Make sense to everyone now? Raquel, okay? Chelsea? Ready? All right. So to generate the graph, I'm going to create a case study. I will start, well, let's do it with megapascal. So I'll start with, we want to go to past 8.58 megapascals, which is the vapor pressure. Let's go to 12 megapascals. So let's start at 0.1 megapascals, the case study. So if I put here 0.1 megapascals, in other words, oh, that's what I have. So, remember how we do case studies? Tools, data book. And now I'm going to insert the variable. The variable I'm going to be changing is the real gas pressure. P low stays where it is. Jonathan B, how are we doing? We're smiling. Does that mean we're totally lost? Where did you lose me? Ricardo, we could have? Right. So, real fluid, pressure. Which now I have set, so it should be in blue, so I should be able to change it. And click another add. What do I want? I want the fugacity. That was in the spreadsheet, so select spreadsheet, and it was in cell A7, if you recall. And click add, and close. You should have those two variables. So pressure and the fugacity calculated in the spreadsheet. And now what do? Case studies. Case studies, click add, and here we'll put this title, fugacity at 300.
What was A7?
It's a fugacity calculation, is what we have calculated. So in this case, it enables only the one it should enable. That's the independent. This is the dependent. Click view. Oh, okay. If I go too fast, let me know. So add variables. Okay, those two variables. Real fluid pressure, spreadsheet A7. Has everybody done that? Emily back there, have you done that? Victor? Jamie? All right. Is it okay? Daniel, okay? All right. So, go to case studies, click add, give it a name, and select the pressure as the independent variable that will be changing, and the spreadsheet calculation as the dependent variable that's how calculated Q gas. And now how do I do the case study? Do you remember?
I don't think we've done this
Yeah,
before.
we never done.
We did it. We did it. You even had a homework in which you changed h as a function. You had to calculate
Did that in
h.
Excel.
We did it in Excel.
And solve it. Yeah, we did solve it for that, not case study.
You sure I gave you a homework that had the case study?
I think you let us do either or, and we all did Excel.
But I did it here with
No,
Unison.
you-
I'm sure I did, guys. I always do it.
Promise you.
Juan's taped every class, I'll pull the footage.
Yeah, what's the bet on that?
Okay, are we caught up then? Okay, that's how you do a case study then. No.
Do you make the real fluid pressure modifiable?
Okay, so click the real fluid. You need to remove the vapor fraction.
Okay.
Delete the vapor fraction and then give the value on pressure. Anybody else? Diana doing okay? Dylan? James? Carlos?
Yeah.
I think I Eric has a big smile. Okay, so let's go back to the spreadsheet. No, to the case study. So tools, data book, and we are here. So then we click view. And here we define low bound, upper bound, and step size. I'll tell you what, to make it simple, let's put low bound 1 megapascal. Well, okay, I guess we can put 0.1. 0.1. High bound, 12 megapascals. I want to go past the vapor pressure, which is 8.58. So I want to see the transition from vapor to liquid. Low pressures will be same if you guys look at the vapor.
When you have to change the from KPA to
Yeah, you were saying megapascal.
Oh, yes. What did I put? Thank you. Thank you. 0.1, not KPA, MPA. Absolutely. Thank you, Charles. Everybody please click the arrow to get megapascals, not kilopascals. Delete the upper bound so it will let me do it. So 0.1 megapascals. It didn't let me because it doesn't let you have lower. So 100 kilopascals low bound, high bound 12, click megapascals, the second entry. Step size 0.1 megapascals. So let's see if I can make it do this. So in terms of kilopascals, 100 kilopascals is the low bound, 12,000 the high bound, 100 kilopascals the step size. And then make a wild guess what I press.
Start.
Got it. And then you click results. Voila. You can see approximately equal to the pressure, and then you have some curvature, and what happens at 8.6 megapascals?
It's flat.
It flattens. There's a transition there. What is that transition?
liquid phase change.
Exactly. Less than 8.6 megapascals.
You mean 6.7?
Less than this, we are vapor. Higher than this, we are liquid. subject. Chris, this is the next subject. That we're going to be talking in a minute. How I calculate the fugacity of a liquid or of a solid. What you do is, you have several approximations. And you can see them all here. The roughest approximation is the vapor pressure at that temperature. So you can see here the fugacity here is about, I don't know, 6.8. The roughest approximation, we know that the vapor pressure is 8.6. Would have been somewhat off. The next approximation, and that's a very standard approximation, is to take a fugacity of the liquid. The fugacity of the saturated liquid or saturated vapors is the same.
Can you say that all again? The last part?
The next approximation is to take the fugacity. Let's say I'm here. I want to find the fugacity of the liquid. The next approximation is to take the fugacity of the saturated liquid. In other words, at this point.
What?
Okay? That's not too bad an approximation for this value. Let's say, well, I want the fugacity of the liquid here. Approximate with this value is not that bad.
Isn't that the vapor pressure?
Yeah. No. That's the fugacity at the vapor pressure. Vapor pressure is this value, 8 point something.
Okay.
You see, if this was totally sloped ideal gas 1, then we would have been there. But because of the curvature, the vapor fugacity is not equal to pressure except at low pressures.
Okay. Yes.
Okay? However, for solids, vapor pressure is excellent approximation because sublimation regime is only for low pressures. So you have low vapor pressure, and for low vapor pressure, fugacity is practically the same as vapor pressure.
Okay.
So for solids, actually, that would be an excellent approximation. Next approximation for liquids would be to correct, it's an integral VdP, this equation here. I'll show you in a minute. To correct for the integral VdP by taking molar volume constant. Molar volume is essentially the density of the liquid. Density of the liquid changes a bit with temperature, but not a lot. Please wait after. So it has to. So the fugacity of the density of the liquid, we take it approximately constant. That's better than here. We assume no change at all with pressure. Here we're going to take that integral VdP with constant V molar. Next best, and that is really, really good, is to take not V molar constant, but to take KT constant. Okay? And then you get an expression for V molar that you can use in the integral. So these are the 4 progressions of modeling, of calculating fugacity of a liquid with increasing accuracy. Let's see how much time I have. So I have about 15 minutes. We will stop here the example, except very quickly, let me show you. Obviously, it's good with the water model. What if I had used a different model? One nice thing is we can very easily switch model. If you click the beaker, go to view fluid packages, and change, let's say, NBS steam to Penn-Robinson. Okay, so I changed to Penn-Robinson. You don't have to do it, just watch what I'm doing. Click, return to simulation environment, say no to the red light. We just need to run the case study again. Tools, data book, case studies, view it, run it again. This is the result with Penn-Robinson model. Not too bad. You can see it's below 7,000.